Hi. Well, let's talk about position and time graphs. Graphs are very important in physics, okay? They can bring us important information about an object that is moving. So when analyzing complex motion, it often is useful to represent the motion in a variety of ways. A motion diagram contains information about an object position at various times. Tables and graphs can also show this same information. So let's plug in data. Data listed on table number 1 can be presented on a position time graph in which time data is plotted on a horizontal axis and position data is plotted on vertical axis. This is very important about position and time. Okay, time is going to be a independent variable. Why? Okay, time doesn't depend of other events on nature. Okay, time is independent. If you stay at Japan or China or Costa Rica or I don't know, United States, time, 1 second time will be the same at any place on the surface on Earth. So time always is going to be the independent variable in a graphic. And the independent variable always is going to be on the x-axis. Okay, that's very important. That's the reason why we can make different type of diagrams or graphs. Always with you, when you have a variable like position, velocity, acceleration, temperature, pressure, and you are studying these variables a long time, time always is going to be the independent variable and will go on the x-axis. So, come on, see the table number 1, right? This is a table about time and position, okay? So time, we will have 6 different values on table, on time, sorry, 1, 2, 3, 4, and 5. And position always is going to be, or 2, sorry, is going to be 6 variables, 0, 5, 10, 15, 20, 25. Okay, so you can plot this data on a graphic. So time is on the x-axis and position is going to be on the y-axis. Okay, so the only thing you have to do is to join two different numbers. 0 with 0, yeah. Oh, let me see. I forgot join 0 and 0. Yeah, we can do now. 0 and 0. Okay, so there it is. 0 and 0. 1 and 5. 2 and 10. 3 and 15. 4 and 20. And 5 and 25. Okay, so that is going to be a graph, a position time graph. please don't forget to put the variable here, okay, and the unit. That's very important. Time, second, position, meters, because we can have another type of dimensional variable. So for example, their time can be hours, or position can be kilometers. Yeah. So it's very important to write the variable always when you do a graph. Okay, so estimating time and position. So notice that the graph is not a picture of the runner's path. The graph line is sloped, but the runner's path was horizontal. Yeah, we are drawing a position time using an example, a runner, okay, a lady runner. So this is very important. Graphs are not a picture of the object that is moving. I can share my screen with you. Okay, here we have the runner, the man. I'm gonna give him a velocity 1.5, for example. Okay, 1.5 to the left. Okay, 1.5. If I play this movement, okay, look at the position time graph. Yeah, it's a line. It's a line, and it's not a picture of the runner. Yeah, like it's a straight line with a slope, while the man or the runner is moving to the wall. Okay, so of course, man is walking or running on the horizontal plane, on the ground, but the position time is a straight line with a slope. Okay, so that means the last paragraph, okay, is not a picture of the object that is moving. Okay, instead, the line represents the most likely positions of the runner at the times between the recorded data points. Okay, very good. Now, continue. Okay, so we can have different equivalent representations. Okay, so you have several different ways to describe motion. Okay, so you have several different ways. You might describe motion using words, pictures, motion diagrams, sorry, data tables, or position time graphs, or maybe equations, or sounds like dun 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 dun. Yeah, I know. It's like oh my god, there's a shark and it's searching me. It's looking at me, so I have to swim very fast to escape from shark. That's a good movie. a good 80 movie. So, okay, so we can represent movement in different ways. All these representations contain information about the runner, for example, okay? However, depending on what you want to learn about an object's motion, okay? Before enter to velocity and speed, I think that we can define instantaneous position first. So instantaneous position is like did you see once when you were young, a child, the coyote and road runner, right? Okay, I will look at them there on the YouTube. Give me a second. Okay. Okay, I will share with you my screen, right? Let me see. Okay, sorry. It's a technical problem here. Okay, so again. The red runner is running and then a pause, okay? A picture, a photograph of the road runner running, okay? That photograph is an instantaneous velocity. Yeah, at this moment right now, the road runner has a velocity, okay? And somebody took the picture, took the photograph, and it's an instantaneous position too. It's in front of the coyote, for example. And another instantaneous. Yeah, that is an instantaneous position and instantaneous. Okay? So instantaneous defined as a position or velocity of an object at a specific time, like a frozen photograph that it was taken. Okay, so back to the lecture. Yeah, okay, so how long, let me see, wait a minute. No, I am here. How long did the runner spend at any location? Each position has been linked to a time, but now, how long did that time last? Okay, so the image that is freezing, how long was that freezing, for example? You could say an instant, but how long is that? If an instant lasts for any finite amount of time, the runner would have stayed at the same position during that time, and she She or he is the road runner. Okay, she would not have been moving. So an instant is not a finite period of time. However, it lasts almost 0 seconds, a tiny, tiny, tiny interval of time. Yeah, that is an instant. Is when and the interval of time goes to 0 seconds. Okay, so exactly we can define an instant like a picture of an object that is moving, a car, a lady, a motorcycle, whatever object that is moving, and we take a picture, then we can have an instantaneous position or velocity, for example. Okay, the symbol X here represents the runner instantaneous position at a particular instant, and is simply called position. Okay, good. So now in this instantaneous position, then we can talk about velocity and speed. Okay, and velocity and speed are instantaneous too. Okay, but suppose you recorded the motion of two joggers on one diagram. The position of jogger wearing red changes more than the jogger wearing blue. For a fixed time interval, the magnitude of the displacement that will be delta x is greater for the jogger in red because it's moving faster. Okay, so as you can see here, we have the graph position. Oh, I forgot. Of course, this is position and this is time. Okay, so position time from red jogger or blue jogger, the difference is the slope. Okay, the slope on a graph position time will have a physics meaning. Okay, so compare the lines representing the joggers in the graph. The slope of the red jogger line is steeper. Okay, no, steeper. Yeah, steeper. Okay, indicating a greater change in position during each time interval. Okay, you find the slope of a line, but first choosing two positions on the line. Okay, two different positions. That's very important. So each position will have a time. So you have to choose 2 points on the straight line. Okay, next, subtract the vertical coordinate of the first point from the vertical coordinate of the second point. After that, you subtract the horizontal coordinate of the first point from the horizontal coordinate of the second point. Yeah, it sounds like difficult, but it's not. Look at the formula. Okay. Okay, so it's a or are two subtractions. Okay. First is the subtraction of position, right? So final position minus initial position will be here above the dividing line, okay? And then final time and initial time will be under the dividing line, okay? So that is an That is the slope on a position time, okay? On a position time graph. Yeah, and the physical meaning of the slope on a position time graph is average velocity, okay? Average velocity. So interpreting the slope of the graph indicates both magnitude and direction, okay? On next graph, sorry, for example, the object has an average of -5 meters by second, okay? We are gonna calculate this 5 over here. Next step, the object started out at a positive position and moves toward the origin. After 4 seconds, it passes the origin and continues moving in the negative direction at the rate of 5 meters by second, okay? So the graph continues after the 4 seconds. Okay, to calculate, let me see. No, I'm gonna calculate here, okay, the average velocity. So velocity and this time, this intervals time, this is very important to know, okay? This point over here and this one are the intersections of the straight line with the axis, okay? So first, this 20 over here, the intersection between the straight line and the y-axis, this point, and it doesn't matter which point do you have, if that point is over the y-axis. Always here, time is gonna be 0 seconds, okay? That 20 is the initial position of the movement, okay? So is x final minus x initial dividing by the final time minus the initial time, right? Okay. So the final position, sorry, will be this one, okay? Here at the intersection of the straight line with the x-axis, okay, the horizontal axis, here position will be 0 at this point, okay? And you have to remember this is important information that I'm giving to you. All the intersections between axis and the straight line have a physical meaning, okay? So first, the intersection with the y-axis, time will be 0, and then the intersection of the straight line with the horizontal axis, position will be 0. So final position will be 0, initial position will be 20, okay, take it easy, 20, because 20, at this point will be 20, no 0, okay, the final time will be 4, and the initial time will be 0. So you can put this on the calculator and will give you -5 meters by seconds, okay? Yeah, I know. There's an important question over here. What is the meaning of that minus that is in front of 5? Okay, of course, it has an interpretation, a physical interpretation, okay? So this minus over here is telling us that the movement of that object is going back to the origin, okay? And then we have another important characteristic here, okay? The intersection of the straight line with the horizontal line, this point over here represents the origin of the movement, always. The intersection of a straight line with an horizontal line or the horizontal axis, that will mean the initial position. If we are talking about a position time graph, please remember that, because when we are gonna see the velocity time graph, of course that this point, this intersection will not mean the origin point of movement, for example, okay? So, excellent. Then, for example, for the red and blue jogger that we had here, for example, okay? So imagine that I have the two different points, the movement of each runner, okay? I will invent, okay, those numbers over here just to put on a number on the slope, okay? So he has a relationship between the slope of the red straight line and the number 2 meters by second, that is the slope, and the blue jogger straight line with the slope here with the number 1 that we already calculate, okay? So remember, I invented these numbers, okay? So imagine, for example, that at this point over here, we have 3 seconds, okay? So 3 is gonna be with 6, okay? I am inventing in this moment the numbers. And 2, let me see, 2 is with 1, okay? 2 is going to be with 1, right? Okay. So excellent. 3 on the blue straight line, for example, 3 is going to be with 3, okay? So yeah, it's difficult to invent here. W jogger, for example, it can be 3 here, and of course that will not be related with this one. So I will put here 1 and here 2. Okay. Yeah. Now it got sense. Yeah. Okay. So this 3 over here with 3 on position, and then 2 by 2. Okay. So I invented these numbers only to given a number from these two slopes of the straight lines, red and blue. That's it. Okay. I will do an example in a few moments. Okay. So the average velocity, okay, the average velocity, note that the slope of the faster runner's line is a greater number, okay? A greater slope indicates a faster speed. That's very important. That's the reason that I wrote this sentence on the green, okay? So notice that. Also notice that the slopes units are meters per second, okay? Average speed is the radio, is the radio, yeah, of an object's change in position to the time interval during which the change occurred. Okay, I will explain this using an example. Okay, so if the object is in uniform motion, so that its speed does not change, then its average velocity is the slope of its position time graph. So for example, to talk about the slope, okay, I'm gonna do an example here, okay? The slope value is the object's average speed, which is the distance traveled by the time taken to travel that distance. For uniform motion, average speed is the absolute value of the slope of the object position time. The combination of an object average speed and the direction in which it is moving is the average velocity. Oh, so back to the example here about -5. So I calculate the slope. The slope is -5. So if I ask speed, which was the speed of the object that is moving, so the speed will be 5 meters per second because minus represent direction. So velocity, that will be 5 meters by seconds. Okay, so I will have to put on here some direction. So I don't know, for example, at the beginning, this point over here, 20, was 20 meters to east, and the object started moving to the west and arrived to the region. So the velocity will be 5 meters per second to the west because the initial position was on the east. If I choose east to be positive, so if I calculate average speed, the sign will means always the direction. In this case, a positive of 5 here will represent 5 meters per second to the east. Okay, I choose the direction. I choose. Okay, so look at this. Speed and velocity both have the same magnitude. 5 meters per second, 5 meters per second is the slope of the position time graph. But the velocity always there is a direction next to it, okay? Always will have a direction next to the magnitude if we talk about velocity, okay? So two quantities are also proportional when displacement is greater during a given time interval. So is average velocity, okay? Average velocity is related to displacement, and speed has a relationship, for example, with distance. So that's the reason why speed is has a scalar and velocity is a vector, right? Okay, so let's do an example before talking about equation of motion. Let's do an example here. I am looking for a white sheet of paper. Oh, there it is one. Okay. There is one. Okay. So we put on the white sheet here, and I will share the problem with you, sharing my screen. Okay, give me a moment. Yeah, there it is. I will share with you the information about the exercise. Okay, there it is. Okay. So the figure shows an object position versus time, right? The letters A to E correspond to various segments of the motion in which the graph has constant slope. Okay, so A, write a realistic motion short story for an object that would have this position. I don't know, maybe it's a runner. Okay, so in interval number, or sorry, the interval A, the runner is running to the east, for example. Okay, and B, there is a, he or she is not moving, and C is running to the opposite direction. Okay, D, the runner is not moving, and E, continue running to the opposite direction when it start moving, for example. Okay, so it can be a graph of a runner. Okay, so B, in which segments is the object at rest? Okay, this is very important. So let's work. Let me see. I have here a pen. Yeah. Okay. So the first question is, in which segments is the object at rest? So I will do the graph here. Okay, it's important because we're going to calculate the slope. Okay, the runner start moving in this position, then goes on the horizontal line, then back to the axis, then you have the D interval, and then E. Okay, E, D, C, B, and A. So at the graph, okay, we have values like number 2, -1. Here is number 2, a -2. Okay, then we have here 10. We have here 4. Here we have 5, 11, this point, and that will be, let me see, 19. Okay, so excellent. This is a position on meters and time on seconds. So the second question is very easy. Segments of the object is at rest. So B is going to be at rest. Why? Okay, let's calculate the velocity, the slope. So final, initial, final. Okay, so remember the formula. Final position minus initial position dividing by final time minus initial time. Okay, so final position will be 2 at B. Initial position will be 2 again. Final time 10, initial time 4. That will give us 0. Yeah. Okay, so an important conclusion here is that when we have the horizontal line, okay, on a position time graph always means that the object is not moving. Okay, the object is not moving. This represents this 0 over here. And of course, D, segment D, we have the same 0 minus 0, 15 minus 11, that will be 0, 2. Okay, so at B and D are the segments that the object is at rest, right? Excellent. So back to the question. C, in which segment or segments is the object moving to the right? Okay, so I will choose, because the problem doesn't say anything, I will choose that this original and initial position over here is going to the right. Okay, so at A, that will be the first interval, I will choose that A is going to the right. So because the problem, it doesn't say anything about this. So A will be, the final position will be 2, the initial position will be -1, final t 4, the initial time 0. So that will be 3 divided by 4, and that will be 0.75 meters by seconds. Look at the positive sign here. Okay, for me, that I choose, positive sign will mean right. Okay, the object on interval A is gonna be, or is gonna be moving to the right direction. Okay, so C, if we calculate C, for example, C is from this point to that one. Okay, final position 0, initial position 2, final time 11, initial time 10. So that will be -2 meters per second. Okay, that minus will represent not right, left. Okay, the object is going to the left. Yeah, then on D segment, the object is not moving, and then E segment, and E, final position -2, initial position 0, final time 19, initial time 15. So that will be -2 dividing by 4. And that will be minus 0.5 meters per second. Okay, so again, here the resultant is giving us -2. So indicates that the body is moving to the left, left, left. So answering the third question, only segment A, the object is moving to the right. Okay, very good. So next question is about, is the speed of the object during segment C greater than or equal to or less than its speed during segment E? Explain. Okay. So I already calculate this. Okay, C and E, if you look the slope of the graph, okay, and C, the slope is -2, right? And remember the slope, I forgot here, there is a mistake. This is a mistake of representation. That is V, velocity, okay, average velocity. I don't know why I wrote C, okay, but yeah, remember the slope is velocity. Yeah. Okay, so velocity, yeah, on the C segment, okay, is -2. And velocity on the E segment, okay, velocity at the E segment will be minus 0.5. So of course, and look at this, and at C or an E, C and E, both intervals, the object is moving to the left, okay? Because its velocity is giving us minus a negative quantity, okay? Yeah, I know the speed, very important, the speed on the C interval is greater than speed at the E interval, okay? Both have the same direction, right? But different speeds, okay? Different speed because, of course, there is 2 and 0.5. Okay, so speed is the number. Velocity is including the direction of movement, right? Only C, no, sorry, only E, no, only A, the object is going to the right because the slope give us a positive quantity, okay? And both B and D, the object is not moving. The reason is that the slope or the average velocity is giving us 0 meters per second, right? Okay, so this was the example, okay? I will do more examples on next videos. So thanks, see you.